Hi everybody. In the past couple videos, we've looked at how entropy changes in physical processes, for example when pressure or volume or temperature changes. In this video, we're going to look at the entropy of atoms and molecules and how entropy changes during chemical reactions. In our previous videos, we've already developed some intuition for how entropy changes as conditions change, and I'd like to review that by asking a couple of questions. First of all, if temperature increases at constant volume, what happens to the entropy? Does it go up or down? I'll give you a few seconds to think about that. The answer is that when temperature increases at constant volume, the entropy increases. You may try to argue this in terms of sort of a hand-wavy explanation about disorder. When you first learn about entropy in general chemistry, you basically learn that it's disorder, and you might try to say that as temperature increases, the atoms are moving around faster and there's more disorder. While this does get you to the right answer, I would strongly encourage you to think in terms of heat transfer. We've defined entropy, ds equals delta Q reversible over T, such that we know that whenever there is heat transfer to a substance, its entropy increases. And in this case, we can use the first law of thermodynamics to determine the sign of heat. If temperature increases, that's a positive delta U. If volume is constant, W equals 0, so we know that Q must be positive. There's heat transfer to the substance, which means its entropy has to increase. My next question is, if volume increases at constant temperature, what happens to the entropy? Does it go up or down? Again, I'll give you a few seconds to think about it. Again, in this case, the entropy increases. And again, you may try to argue this in terms of disorder. If you give a substance more volume, it has more disorder to move around, so the entropy must increase. Again, this gets you to the right answer, but I would encourage you to think in terms of heat. In this case, with constant temperature, delta U equals 0, if volume increases, then W is negative, meaning that Q has to be positive. So again, heat transfer to the substance means that the change in entropy is positive. Now we arrive at a question that's more the focus of this video. How can we hope to compare the entropies of two different substances, for example helium and xenon, under the same conditions? We really haven't developed the tools to answer this question yet. It's hard to argue that there's a difference in order or disorder between helium and xenon. And no amount of heat transfer is going to get you from helium to xenon. So we need to think about this a little bit differently. When we first talked about entropy in this course, we posed it in terms of numbers of microstates, numbers of different ways that you can occupy the energy levels. And that's what we're going to do here. Helium and xenon are both noble gases, so they both behave approximately as monatomic ideal gases, and their energy levels are determined by the translational energies of the particle-in-a-box model. You've seen this expression for the particle-in-a-box model before. The energy levels are h squared over 8ma squared, where m is the mass of the atom, a is the edge length of the box, and nx, ny, and nz are the three quantum numbers. In this expression, the main difference between helium and xenon is their mass. Xenon is heavier than helium, meaning that the denominator of this expression is larger for xenon, and the energy levels in xenon are closer together than those of helium. I'll illustrate the situation schematically like this. I don't mean to imply that the energy levels are actually equally spaced, or that there's no degeneracy. Neither of those things are true. I'm just reminding you that the energy levels of xenon are closer together than those of helium. So what does that mean in terms of entropy? It means that at a given temperature and volume, more energy levels are occupied for xenon because they're closer together, and therefore there are more different ways that the xenon atoms can be arranged in the available energy states. In a sense, you can say that there is more disorder in xenon, where we're talking about the disorder of the energy states that can be occupied. Putting all of this together, xenon, the heavier element, has more entropy than helium. Notice that this viewpoint of thinking of entropy as disorder in the number of energy levels that can be occupied is consistent with everything that we've said about changes in temperature and volume. If you think about how changing temperature would affect this picture, if you increase the temperature, more of these energy levels are accessible, which would lead to more entropy. And that's consistent with what we said before. We said that higher temperature means more entropy. If you think about changes in volume, increasing the volume increases the A term in the particle in a box and puts the energy levels closer together. So increasing the volume, again, means more energy levels are accessible because the energy levels are closer together. So more volume means more entropy, consistent with what we said before. All of this fits into the same big picture. If we consider our other models of motion in quantum mechanics, we can also compare the entropies of diatomic molecules. I've shown here the expressions not only for the translational particle in a box energies, but also for the rotational rigid rotor energies and the vibrational harmonic oscillator energies. And you can look at the various terms in these expressions and see how different molecules would compare. Specifically, I'll point out that in both the rotational and vibrational energies, larger reduced mass, larger mu, puts the energy levels closer together, and therefore increases entropy. I'll give you a few seconds to practice this. See if you can predict which molecule in each pair would have more entropy at the same conditions. Diatomic fluorine versus diatomic iodine, and HF versus HI. I'll give you a few seconds to think about that. I've highlighted the correct answers here. When comparing fluorine and iodine, really all signs point to iodine having energy levels that are closer together. Iodine has the larger total mass, so translational energy levels that are closer together, and iodine has the larger reduced mass, meaning that the rotational and vibrational energy levels are closer together. With HF versus HI has the significantly larger total mass, so the translational energy levels are closer together. The two molecules have pretty much the same reduced mass, because the reduced mass approaches the mass of hydrogen. But there's still other factors, for example the bond length, where HI has a longer bond length than HF, and therefore a larger denominator in the rotational energy, that point to HI having energy levels that are closer together, and more entropy. Sometimes, even when the masses of two molecules are equal, it's possible to predict their relative entropies. I'll give you a few seconds to think about the two molecules on this slide, and see if you can predict which one might have a larger entropy. It turns out that the molecule on the left, acetone, has more entropy. The key idea here is that acetone is a less rigid molecule. It has more freedom to rotate around, whereas the molecule on the right is more locked in place. So you can make sort of a hand-wavy argument about disorder, how the molecule that's more free to rotate has more disorder in its conformation. But you can also be more precise about their energy levels. The less rigid molecule, acetone, has more vibrational modes that have low frequencies, so vibrational energy levels that are close together, which leads it to have more entropy. So hopefully you can now see that all of these comparisons of entropy fit into a big picture, where it is true, as you learned in general chemistry, that entropy is a sort of disorder. But it's important for us to realize now that the disorder that we're talking about is the ability to populate many different energy levels. Next, I'd like to circle back to the third law of thermodynamics and talk about kind of an interesting case where the third law appears to break down. In the previous video, we said that the third law of thermodynamics tells us that at absolute zero temperature, a perfect crystal has zero entropy. But we also mentioned that the third law assumes that there's no degeneracy in the ground state of that perfect crystal. Suppose we have a crystal of solid carbon monoxide, which looks like this. It's a packing of CO molecules where each CO molecule has a specific orientation, with carbon at one end and oxygen at the other end. Because carbon monoxide has a relatively small dipole, it's almost equally energetically stable to have the CO molecule oriented one way versus the other way. So even in very low temperature carbon monoxide crystals, the CO molecules can fairly easily flip, What that means is that even though there is one true energetic ground state, one structure that has the lowest energy, we see what's called residual entropy down near absolute zero in experiments, meaning the CO molecules within the crystal have essentially a random orientation, and therefore the crystal has entropy. Let's see if we can figure out what the molar entropy of carbon monoxide actually is, down to 0 Kelvin. So, if we want to find the molar entropy, we're looking at 1 mole of CO, and every CO molecule has 2 possible orientations that we're saying are equal in energy. If every one of those molecules has 2 choices, 2 possible orientations, and there are Avogadro's number of molecules, then the number of microstates is going to be 2 raised to the power of Avogadro's number, which really is an unimaginably huge number. We can then find the amount of entropy in this 1 mole of carbon monoxide using the Boltzmann entropy equation. Entropy equals Kb times the natural log of the number of microstates. We'll plug in our number of microstates, 2 to the Avogadro's number, and then we can use our log rules to bring Avogadro's number out front. So we have Avogadro's number times the Boltzmann constant times the natural log of 2, and hopefully you recognize Avogadro's number times the Boltzmann constant as being equal to the gas constant R. So even down to absolute zero temperature, 1 mole of carbon monoxide is going to have some entropy that's approximately equal to R times the natural log of 2. When you look at that numerically, it's about 5.7 joules per mole Kelvin, which isn't a huge amount of entropy, but it is measurable, so this is significant. At this point, we've established that every atom or molecule has a characteristic entropy under given conditions. Like standard enthalpies of formation, it's often possible to look up standard molar entropies in the backs of textbooks. A standard molar entropy is the entropy of 1 mole of a substance at 25 degrees Celsius and 1 bar, and these are often tabulated. And because entropy is a state function, if we're interested in finding delta S of a reaction, the change in entropy during a reaction, we can subtract the entropies of the products minus the entropies of the reactants. In equation form, our approach would look like this. For a general reaction where A moles of A react with B moles of B to form Y moles of Y and Z moles of Z, the standard entropy of reaction would be equal to the standard molar entropies of the products minus the standard molar entropies of the reactants, with everything multiplied by their stoichiometric coefficients. This equation makes things look maybe more complicated than they are. You're basically doing exactly the same thing that you do to find delta H of a reaction, just products minus reactants. To give us some practice with this idea, I'd like to look at an example problem from Macquarie's textbook. In this problem, we're given the standard molar entropies of a variety of elements and compounds, and we're asked to find the standard entropies of reaction for each of these 3 reactions. Before we do that, I'd like to point out a couple things about the standard molar entropies that are listed at the bottom of the slide. First of all, notice that all of them are positive and none of them are 0. These are the absolute entropies of these substances, not entropies of formation. So, for something like hydrogen or carbon or oxygen, we don't define the entropy as 0. We actually list the true absolute entropy, so they're all positive. Also notice that in general, gases have more entropy than liquids, which have more entropy than solids. This relates to the fact that gases have the most freedom for translational motion. Or, if you'd like to think about it in sort of general chemistry terms, gases have the most disorder, because they can move around the most. So, if you'd like to get some practice solving this sort of problem, I would encourage you to hit pause and take some time to actually calculate the entropies of reaction for each of these 3 reactions. But I'll move ahead and animate the answers in. And one of the reasons I wanted to show this problem is that we can actually kind of understand the trends qualitatively. Notice that the first reaction has a very negative entropy of reaction, the second reaction has a slightly less positive entropy of reaction, and then the third reaction is also a little bit negative. We can actually understand qualitatively why these numbers are what they are. As we said, gases tend to have more entropy than liquids and solids. So if we're interested in delta S of a reaction, we can think mostly about the change in the number of moles of gas. In the first reaction, we start off with 3 moles of gas on the left and end up with no moles of gas. In other words, we lose 3 moles of gas, so the entropy decreases pretty significantly. In the second reaction, we start with no moles of gas and end up with 2, so the entropy increases, a little bit less than the first one decreased. And then in the third reaction, we start with 3 moles of gas and end up with 2, so we lost 1 mole of gas. The entropy is negative, but not as negative as the other reactions were. So, just a couple of takeaways from this problem. First of all, remember that standard molar entropies are all positive. They're not zero for pure elements, because these are not entropies of formation. And also remember that the changes in entropy during a reaction are due primarily to changes in the number of moles of gas. As we come to the end of our series of videos about entropy, I just want to demonstrate one more thing that brings together a lot of ideas that we've learned in this course. I'd like to show that we can analytically find the molar entropy of an ideal gas from its partition function. I'm only going to give a broad overview of this derivation here and skip a lot of details, so it's okay that you won't understand quite every step. If you're interested in following along with every step, I would encourage you to refer to the textbook. We're going to start with something that we said in our first entropy video, and that's that we can use the Boltzmann entropy formula to express entropy in terms of the partition function and total energy. This is an equation that we saw several videos ago. We can then further expand the total energy in terms of the partition function, with ideas that we developed in our statistical mechanics unit. Here we make that substitution and substitute energy with kBt squared times the partial derivative of the natural log of the partition function with respect to temperature. That's another equation that we saw several chapters ago. Then we can use the fact that we have n indistinguishable particles in an ideal gas in order to express capital Q, the partition function of the overall system, in terms of lowercase q, the partition function of one atom. This is a step that's derived in more detail in the textbook. We end up with an expression like this. Now we have entropy in terms of lowercase q, the partition function of a single atom, and capital N, the number of atoms. Back in our statistical mechanics unit, we thought a lot about what lowercase q is for various kinds of ideal gases. So now we're going to substitute in lowercase q, the partition function of a monatomic ideal gas atom. So for 1 mole of a monatomic ideal gas, where the number of particles is Avogadro's number, and the partition function lowercase q is the translational partition function of a monatomic ideal gas, we get an expression for molar entropy in terms of temperature, volume, and the mass of an atom. The specifics of this expression aren't important. You certainly don't need to know this expression or memorize it, but there are a couple of things that I want to emphasize. First of all, let's think back on what we've done here. We've started with just the energy levels of an ideal gas atom, and we found this important macroscopic quantity, the molar entropy of an ideal gas. So we've really developed a lot of ideas in this course. I also want to point out that when you stare at this expression for long enough, there are some aspects of it that we can understand. Notice that mass, temperature, and volume are all in the numerator of this expression, which means that as we expected, larger mass, higher temperature, and larger volume all translate to a substance having more entropy. When we plug numbers into this expression using the mass of a helium atom and 25 degrees Celsius and 1 bar, we find a standard molar entropy of helium of 126 joules per mole Kelvin, which perfectly matches the experimental value. So all of this really does work. And finally, I'll point out that if we wanted to do something similar for polyatomic molecules, we would also have to use the other terms in the partition function for rotational energy and vibrational energy, which would lead to more entropy. I'll end the video with a couple of takeaway messages. As we've seen, some factors that correlate with higher entropy are higher temperature, larger volume, a substance being in the gas phase, and closely spaced energy levels, which come from factors like larger mass and structural freedom and things like that. And in a chemical reaction, the change in entropy, the entropy of reaction, is the difference between the entropies of reactants and products, and it depends strongly on the change in the number of moles of gas. That's all for now, and that brings us to the end of our series of videos about entropy. Now we're in a position to put together the ideas of enthalpy and entropy, and to think about what makes a chemical or physical process spontaneous.